that, and then we need to move forward. I'm setting this problem set for Monday. Okay, so that we can turn in homework on Monday, and I could do it Monday. And one of the things that I want you to see here is that these two have very similar. By the way, if you look at my lecture notes online, I have some typos that have to be fixed. So what's on the board here is correct. What's in my lecture notes is not correct. So I have to, so if you're relying on those a lot, you'll see that you'll have to pay attention to some of the mistakes that I have. So we talked about capacitors. And when I look at capacitors here, we have Ohm's law, which I call the capacitor equation, right, that relates the current to the voltage. And one of the things that we've discussed here is that the voltage of a capacitor cannot change instantaneously. Why? Because we have that RC time. The RC time doesn't allow you to sort of change instantaneously. Not true of the current. The current can change instantaneously, and under a few exceptions it won't, but the vast majority of the time it does change instantaneously. And you'll see that any time I have a fully charged capacitor, it acts like an open. So I can literally replace it as an open. So when I say these two statements, this is what I mean. So if I'm thinking about a capacitor that's uncharged, and then suddenly I throw a switch, as I throw that switch, that voltage can then, as it starts to increase, but at these connections before and after the switch, they're exactly the same. So that's a boundary condition, actually. But when I look at the inductor current, there's a discontinuity. And because there's a discontinuity, these two can't be the same in general. The same thing goes with an inductor. An inductor from Faraday's law can be written this way. Okay, so when I look at an inductor here, it's also its Ohm's law, but you can see that the voltage and the current are reversed from the capacitor equation. Now, if I have a fully saturated inductor, you can imagine it having a lot of turns. And if I have a lot of turns, you would expect that if I change the voltage in the circuit, that the current coming in, even though it's changing at the initial winding, it has to sort of like wind itself all the way through. And as a consequence, that current has to be the same. You can also think of it as an analogy of water flow. If I have water in a water inductor, and then I suddenly change the water pressure, well, it takes time for that water pressure to sort of like pulse its way through. Right? If I have a long enough hose, even though I changed it, it's still coming out at the same, volume rate. The same thing happens here. So the current can't change instantaneously, so that means at any change in the circuit, it has to be the same. Not true about the voltage of the inductor. And by the way, you're seeing this in the PLC, where I'm asking you to sort of like piece-spice this, piece-spice that. You can't measure these guys because they happen what? Instantaneously. They happen what? Instantaneously. So the voltage of the inductor can change instantaneously. So if I have a fully current saturated inductor, then it acts like a short. That means that there's no voltage drop about that. Right? If I have no change in current, then the voltage across this must be zero, because the currents are constant. Now, just as a very light example where we're headed here, what we want to do here is that, let's look at this example here. So looking at example 7.2 here, it says that the current in a bi-Henry inductor is given by this. So you know that I of t is either 0 or 4 sine 2t. And this is and then it looks like that. So what they're asking you to do here, so just to make sure that we're talking about proper units, I'm going to say that these are units of amps. So the question I'm asking you here is that I want you to determine power as a function of time and energy as a function of time, right? So this is function of time. So one of the things that I give here is that I have a hint. Right? If I look at this hint here, I'm going to tell you that there's a identity that looks something like this that we can use. So you have a trig identity that we have to use here, which will be useful when we do this calculation. So I'm just going to do that because I want to get to the other examples. This is sort of like to help you with the problem sets. Just to sort of like remind you very easily about what's going on. So what do I mean by power? Power has to be what? Voltage times current. What do I mean by energy? Is the integral of the power. Okay? So when I'm looking at these things, we gotta do that here. So the first thing that I would look at here is that I'm going to call this A, and I'm going to ask, what is this guy equal to? Right? So you have to calculate this term right here. Okay? You have to calculate this term. So now I have the current, but to get the voltage of the inductor, I got to do what? I got to use that relationship. So I don't have to consider the 0 point, but I got to consider this point right here. So if I look at this power here, you can see that the voltage of the inductor has to be this guy right here. And so I'm really taking the derivative of this term right here. So I have, what's my inductance? It's a 5 Henry. Now let's take the derivative of this guy. You can see that I have a 4 here. That's a constant, so I'm going to pull it out. Then I got to take the derivative of sine. But then you can see that I have an argument of 2t. So the chain rule says that I'm going to bring that 2 out. So if I take the derivative of sine 2t with that 4, it's going to be what? I'm going to get 8 times cosine of 2t. So I then should get 8 cosine of 2t. So that's what's giving me what the power is. And note that if I multiply units, I got a Henry times what? An amp per second. So therefore, that should give me units of volts. Just to make sure, since Henry is the SI unit for inductance, then if I multiply all those, it should give me units of volts. So then, the power as a function of t then, you'll see then will be 40 cosine of 2t times, right, the current, but the current is this guy here, which will be 4 sine of 2t. So if I multiply this guy out here, you're going to see here that I'm going to get what? I'm going to get 80, and then I have this trig relationship. Thank you. So I got 160 here. And then you can see here that I have this relationship right here. So check this out. I got cosine of A, sine of B, right? Cosine of A, sine of B. So you can see that there's this term here that's going to cancel out because I got the same argument. So that means here I got a 2 factor that I got to pull out of this guy. So if I pull out this 2 factor, this goes to 80, right? So this should give me 160. Actually, let me write this slightly different. So I'm going to get 80, and then I have the 2, right? So look at that. I got 2 times this, which then gives me this identity. So then I'm going to get sine of 2t plus 2t plus the sine of 2t minus 2t. And then you can see that this term immediately goes to 0 because I got the sine of 0. Why am I doing this? You're going to have trig identities that you've got to do on the problem set. So then that means that the power as a function is then going to be 80 sine of 4t. Now why do I care about doing this? It turns out that if you do this, I don't have to deal with integrating this and this, which is a little bit messy. That's the only reason. Because then you get cosine squared. Well, it depends on how you do it. There's lots of ways to do that. But that's a lot easier to integrate than that. That's all I'm saying. Not a lot, but that's a nice identity to do that. So now if I'm looking at the energy here, so if I look at B here, the energy in inductor is then this work function where I got to integrate the power as a function of time here. So since I want this as a function of time, I know that I'm starting off at 0, that's when the current is 0, and then I'm going to integrate this to a factor of t. Okay? So if I just plug in this value here, you're going to see here that I'm going to get 80 sine of 4t dt. So if I integrate sine here, you know I'm going to get a cosine from this term. Okay? So let's look at this. So if I do this, so if I do the opposite of the antiderivative of sine, I should get what? A minus sign. Now if I do some substitution, you see that I'm going to get that 4 divided by this guy. So I should get 4, and I should get cosine of 4t from 0 to t. And if I just plug this in here, you're going to see that that 0, when I plug it in, is going to give me 1, but it's going to give me negative 1. So I then should have what? If I bring this minus sign, I should have 1 minus cosine of 4t. So then I should get 20, 1 minus cosine of 4t. And that should give me the energy as a function of time. I think that's right. Did I miss something?
Cosine of 0 is 1, so negative 20 times 1.
Is that okay?
I think it needs to be negative 1.
No, but I remember I got that negative sign right here.
Right, but the cosine of 0 is 1.
Yeah, but remember, I take the subtraction, right? It would be cosine of 4t minus cosine of 0. Okay. Now we get to where we need to be. This whole thing is just to remind you, very lightly, what an inductor and what a capacitor is. So why are we here? We need to find the initial values of a first order circuit and a second order circuit. So let's talk about that. So our job here is that we now want to look at initial values of circuits with switches. This is, as far as I'm concerned, this is the only reason why we are in this chapter. So what you're going to find here is that now we need to start talking about what are called initial conditions. And I'm going to call this IC, or IC. And a lot of the times what you're going to find here is that the initial conditions will depend on whether it's a first order circuit, first order differential equation, or a second order circuit, a second order differential equation. And so if I look at a first order circuit, what you're going to see here is that as we get into chapter 8, you're going to end up with an equation that may look something like this loosely. And what we know here is that because this is a first order circuit, you get one arbitrary constant. So this implies here that to solve one initial condition must be determined. Okay, that's what you learned in differential equations. And what you're finding out is that this is what happens here. What you find out here, so if I have a cap, that means I'm looking at this guy right there. We look at V0 minus. Here, let me step back. Let me say this differently. Okay. So what you're going to find here, so let me draw a very generic circuit. So if I look at a circuit, let's say that looks something like this. And I have a switch, and I have a capacitor, and I have a resistor in the circuit. When I throw this switch at t equals to 0, what you're going to find here is that we are only interested in t greater than or equal to 0. I typically am not interested in what happened beforehand. But the problem is, once I throw the switch, I got to solve the first order differential equation. But nature has been kind to us. Why has nature been kind to us? Because we know that capacitors cannot change the voltage instantaneously. As a consequence, right before the switch is thrown is also equal to the voltage after the switch is thrown. So by finding the voltage before the switch is thrown, I actually know what happens at 0 plus or minus 0, at t greater than or equal to 0. So that's why I say nature has been kind here, is because this is easier to solve. And what that does here is that it sets an initial condition. It sets an initial condition so that voltage there can then determine this one constant that I don't know how to do. Okay? So that's really nice. By the way, the same thing happens with the inductor. If I have an inductor equation, okay, if I have an inductor circuit, actually, let me draw it up here. Maybe I have a source like this, and I have something like this. The same type of scenario happens. And what I mean by the same type of scenario happens here is that maybe I should have put a switch here. So now, when I throw this switch at t equal to 0, again, I have this one, arbitrary parameter. So what we say here is that it's not this arbitrary parameter. Maybe I should put this in quotes, but it's the parameter that you need. And again, what happens before and after the switch, I can determine. Even though I'm only interested in what happens after the switch is thrown, but this is a superb condition here. Now, as I go to second order circuits, things get more complicated. And they get more complicated in a hurry. And so now I have second order circuits. So when I have second order circuits, you could imagine that I could set up a scenario where I get this now. So that means the following thing here. So in differential equations, they tell you if you have a second ordered circuit, that you have two arbitrary constants. Right? So here, what this tells us here is this, that to solve completely, there are two constants. And they typically tell you that it's this guy at some time, typically at 0 plus, and this time at 0 plus. Assuming that I have some arbitrary circuit where it looks, let's say that I have a circuit that looks like this. So I have a switch, I have a resistor, and I have a capacitor like this. So now, what I'm doing here is that I'm throwing the switch here. Let's say at t equal to 0. Well, what you're going to find here is that, one, you'll never see a circuit this nice from me. Okay? They're way more complicated than this. And there's a problem here. Because we have more complicated circuits, the statement is not exactly correct. Because just think about this here. If I had a first order circuit, what did I need to know? The initial condition of the cap, right? I needed to know that voltage in order to apply it here after the switch is thrown. If I have an inductor, I needed to know what the current was before the switch was thrown. And so what happens here is that we need both VC 0 and IL of 0. So if I have an inductor and I have a capacitor in the circuit, then that means here that I need those two. See, this circuit's a little bit too trivial. Maybe we could do something like this. Okay, that looks a little bit better. Because the other one is just a plain lie, right? We know that if that thing is open, the inductor has to have a 0 to it. But now, we don't know that. Maybe there's in those boxes, there are power supplies, or current sources, or dependent sources. You'll see those. So the thing about it is that, no, I need two of them. I need a minimum of two of these guys here. I need a minimum of what? One of these. So then we also need the following thing here. We're going to need either dV dt or di dt. I'm going to need at least one of these things. So right now, you know how they say two constants, as far as you're concerned, you got three, right? You got this guy, two, one of these or one of these, and then you get the worst case, situation. That means that you need both dv, dt, and di, dt. So there are circuits that I need how many constants? 1, 2, 3, 4. And just to solve for the initial conditions, you'll see that you'll have a system of equations. And the nice thing about the circuits that we deal with is that how you derive these are closely related to how you derive that. And that's something that you don't do in your differential equations class, but that's something that you're going to have to get really good at. And so it's a little bit of a shock here initially. So you'll have to sort of like just hang on to your seats. Try not to fall over. Right? That's where we're headed. So what is our job here in chapter 7? This whole thing that we're talking about is actually like one step in solving second order differential equations. Okay? I think a lot of times you'll see that this and this can be challenging, but when you got these, you got to pay really close attention. And the detail involved in you solving these circuits is complicated. There's a lot of things, a lot of little steps, but I promise you this, that overall through the years, the majority of the students say, this is the best part of the course. This is the most fun of the course. And all of this stuff may seem like folklore, and you know what ends up happening? You can take this into the lab and measure it. And one of the most challenging labs is the second order circuit. Let me tell you about that second order circuit. The measuring is easy. It's the calculation that's hard. You'll probably spend 5 or 6 hours solving this differential equation because you're not going to know what you're doing. And then after you finish that, my experience is you're a master of finding the differential equation, finding these initial conditions. So you just got to trust that as we go along, you will get it. But my experience is that you won't get it till right before the exam. Right before the exam. Okay. So, what are we going to do here? So let's look at strategies. Not strategies. Let's talk about process for determining initial conditions. So the first thing I want you to pay attention to that cannot use mesh or node. Okay, so I don't know, should I pass off the tissue now? No more mesh and node. You're going to see that the best way in thinking is simple circuits. But that doesn't mean that you throw away the ideas of mesh and node. You have that thinking. You want to keep this type of thinking. It's super important to keep that. Super, super, super important. If you're lost, draw in the nodes. Look for circles or paths or loops that make sense in how you apply KVL. It's that kind of thinking that really helps you here. So what you're going to find here is that you must use KVL and KCL thinking with simple circuits. Right? So you're going to really be looking at loops and KCL nodes here. And you're going to find here is that when you do that, you also have to use the capacitor / inductor equations. So you're going to have to convert a lot of the times what's going on. That means you're going to have to relate these guys here. You're going to have to relate this guy here. Oops, I think I wrote that wrong. This should be VC. This should be IC. You're going to have to constantly employ these guys. And one of our jobs here is that you're going to find out here, too, is that sort of like for second order circuits, which is what you're going to be doing right now, what you want to pay attention to is that this is the rule of thumb. You're going to have to do this. So if I have a second order circuit here, is that you want to apply KCL and relate IC to IL. You want to relate the current of the inductor to the current of the capacitor. Now remember, these circuits are not in steady state. They're changing. So we want to look at how these change. Then you want to go in and you want to apply KVL to relate VC to VL. So what this does here is that this essentially says that our primary goal is to solve for VC of 0 plus, IL of 0 plus. Okay? So the way we do that is we look at what? We look back at these conditions and we go like, wait a minute, we know these conditions. What happened before the circuit? The switch was thrown in the circuit. So these is what we're after. The other thing that we're after here is IC at 0 plus, VL at 0 plus. And this is the challenging part. Because these guys do what? They form the discontinuities in the circuit when you're actually looking at these things. And what you're seeing here is that this means here that you're going to have to look at the rest of the circuit. So when I'm looking at these guys right here, what we do here is that we look at how the rest of the circuit determines these. And you're going to see that these guys are the challenging part of the circuit. Okay? This is the challenging part of the circuit. What you're going to find here is that a lot of the times you're going to get two equations and two unknowns. Okay? And when I say two equations and two unknowns, then I'm talking about this case right here, the worst case scenario. So, shall we? So what we want to do now is we want to go through two circuits and sort of like set these guys up. Okay? So we're going to go through 2 circuits here. So let me erase and let's do that. So here's the first circuit. So we're now looking at so if I look at the circuit here, imagine that I have this circuit right here. So I have a 12 volt with the switch, and then I have a 3 ohm with the capacitor, and I have an inductor with the resistor in series. So I have a 3 ohm, I have a 6 Henry inductor, I have a 50 millifarad, and then I have a 6 ohm. So then I'm going to say that the switch opens at t equal to 0. What do I want you to do? I want you to determine everything. That means I want to know what VC at 0 plus is, what is IL at 0 plus is, what is IC at 0 plus, and what is BL at 0 plus. What are these guys right here, right? So I want you to determine these guys right here. Give me a minute. Okay, let me give you a minute to actually start to look at that.
Yeah, but how would you write? Sorry.
Okay, let's look at this thing here. Okay, so the first thing that I'm going to look at here is that this is what I'm interested in. The fact that the capacitor and the inductor voltage and current can't change instantaneously means I want to calculate 0 minus for these guys. Okay? So when I look at this guy here, it tells me always assume the circuit is at steady state at t equal to 0 minus. So here we go. So at t equal to 0 minus, that means I've really had how much time? It went from minus infinity to 0 minus. So that means there's more than enough time for this to reach steady state, which is an open, and that is a short. So if I look at the circuit here, then I have a circuit that looks like this. So in steady state, I have a 3 ohm, and I have a short, and I have this resistor. So when I look at this, I see that I have VC of 0 minus, and then I have this inductor current at 0 minus. So when I look at these guys here, I see what? Well, I see that the current of the inductor I only have one branch here, so that means it's got to be what? 12 divided by the sum of these, so it should be 12 divided by 9, which should be 4/3. So if I look at this guy here, so if I look at the IL of 0 minus, it should be 12 divided by 3 plus 6, right? That is 4/3, right? Of an M. Which immediately tells me, remember, I don't care about the minus, I care about the plus. It tells me that I now know the current in the inductor after it's been thrown. The switch has been thrown, that is. And if I look at VC, you can see that VC is parallel to the 6 ohm resistor. Well, since I know the current, I can then get the voltage across the 6 ohm resistor, which means it has to be the same as the 6 ohm resistor at 0 minus. And so when I look at this here, then you can see that according to Ohm's law, it should be 6 times 4 over 3, which gives me what? 8 volts. Which means then, like I said before, I really don't care about before, I care about afterwards. Yes, sir.
Are we accounting for the resistance in the inductor, or is that
No, a
not?
perfect inductor has no resistance. You could imagine it's superconducting material.
Right.
Okay? So the question is, what is the current of the capacitor? At 0 minus? 0, right? Because it's an open. What is the current of the inductor? The voltage across the inductor? At 0 minus? 0. Because I'm in steady state. The inductor equation says if I have a constant current in that circuit, then I have that. Okay? This does not help me to calculate these. Why? They're not the same. So now, what happens here? Now the switch is thrown. And now my circuit looks like this here. Right? I have, this guy has now been disconnected, so I got an open. So right away, I have this, and I have this inductor like this. So the first thing that I realize here is that this resistor is what? Dead. Okay? What do I know after the circuit here? Well, for starters here, the voltage of the cap can't change. So I'm going to come over here. What's the voltage of the cap afterwards? Well, it has to be 8 volts. It's still 8 volts. However, the current has changed. Which direction is the current? Down. It's a passive element. So therefore, the current of the cap must be looking like that. Now, when I look at the voltage, if I look at the inductor, well, the current of the inductor can't change. So if I look at this current here, this guy tells me that the current of the inductor here at 0 plus must be 4/3 amp. Right? So I know I have a 6 ohm resistor here, but I know that the voltage of the inductor has to be changing. We would expect it to change. So now, how do I determine IC? How do I determine VL? I look at what? The rest of the circuit. The circuit is going to tell me that. So right away, we can, right, this is a fairly nice circuit here, right? If I make this ground, we know that this has to be what? 8 volts. So if that's 8 volts, you know here right away that this guy, since the current can't change, we know that the current through the 6 ohm resistor must be 4/3. So when I look at this guy here, what you're finding here is according to this, okay, I'm thinking too many things here. So now, the B6 ohm at 0 plus must be what? 6 times 4/3, but that means that that has to be what? 8 volts. So in this case here, if this is 8 volts, and that's 8 volts, the inductor voltage must be 0 at 0 plus. So in this case here, we're not seeing a change in the voltage of the inductor. Okay? It started at 0, and it's 0 afterwards. But now, what about the current of the, what about the current? So I got that voltage, I need that current. Look at the currents. How am I going to calculate the currents? Well, let's look at KCL. What does KCL say? That current, plus that current must be what? 0. Right? That's what we mean by passive, right? The currents are coming down, they're going into this node. So let's draw another node here just to make you happy. Right? And you can see here, KCL at bottom node is what? IC at 0 plus equals IL at 0 plus. We know this current is going this way, so then this implies here that the current of C must be minus IL of 0, so it's got to be 4/3 amps.
So why did you draw the current in the capacitor that way to begin with, since they're in series?
Wait a minute. I thought capacitors were passive. Is there an EMF source in a capacitor that moves charge from the negative plate up to the positive? No. When I think of a capacitor, I think of 2 plates, and I have an insulator. There's nothing that I'm aware of that takes charge from here and pushes it up to there. Passive elements have current that flow from where? Positive to negative. So if I plot this thing, look at the plot. Now, I don't know what these guys are looking like, but I can tell you about this, that if I was to plot the current of the capacitor as a function of t, what's it coming at as? The current of the capacitor is what? 0. It's coming in at 0, and then what does it do? As soon as the switch gets thrown, it jumps where? To minus 4/3 amp, and that's 0. You see how there's a discontinuity jump? The inductor current changed instantaneously. But these guys can't, right? No, these guys can't. They're going to be the same. So if I draw them, you're going to see that wherever the voltage is, like I don't know what they look like. We'd have to calculate that. Let's say if I look at the voltage of the capacitor, now the voltage of the capacitor starts off at 8 volts. Let me draw this a little bit further down. So what happens here? I know that the voltage of the capacitor must come in, and it has to do this, right? It comes in at 8 volts. Now, look at the picture here. Is the capacitor charging up, or is it discharging? It's discharging. Because there's nothing to supply it. So what's it going to look like? It should look something like this. Going to 0. But look at this point right here. The minus and the plus give me what? 8 volts. You know, I feel like we should come back and look at this thing again. Okay? I think that there's a lot of misconceptions about that. So let's just deal with it right now. So that way we don't have to talk about it again. Yes?
I think you said it's passive, so the current's going from positive to negative, but then you calculate and get a negative current, so the current's actually going from the negative to positive.
I'm just applying KCL.
Yeah, like that.
And let me tell you, if you do it the way you're saying it in the future, watch you get incorrect answers. Watch you apply that kind of thinking that you just had, and then go try to measure a circuit like you're going to do in the future. You know what you're going to get? Incorrect answers every single time. Let's just deal with this thing once and for all. What is the best mechanical battery that I could think of? It's the Van de Graaff. Right? If I think about a Van de Graaff, I have what? I have 2 rollers, effectively. And what do I have? I have a belt. Okay, so what happens here, as you already know, if you rub something, you're going to get charge separation, right? I have 2 inductors. I rub them. I essentially use a strong insulator, rubs off negative charge off the weaker insulator, and charge gets separated. Here I go. There's rubbing going on right here. Right? I could say, here's my belt right here. So what happens? As I rub, I do what? I take negative charge off of here. As I take negative, oh, wait a minute. Let's do positive charge. Okay? Because that's what our batteries say. So I pull positive charge off of here, and what do? I move it in that direction. As I move it in that direction, what did I take off of? I took positive charge off of here, so what do I have to have? A negative plate. Right? And as I bring positive charge onto this plate, what do I get? I put on positive charge. Right? So when I look at how I create a battery, inside I essentially have this mechanical analogy. So the motor, as soon as it gets into the steady state where I got to look at the sort of like the forces that sort of like repel these charges. So I deposit charge onto here, and then I build this. So this Van de Graaff is the mechanical EMF. So far, so good? Let's look at a capacitor now. I have a capacitor. Here's my insulator. So if I had my insulator, let's have charge now coming in. So I have charge. I have a wire coming in. And if I have positive charge coming in, then I start to build charge onto my plate. And as a reason of induction, I get negative charge here. Is there charge going through that insulator? Hopefully not. Is there ever a situation where I'm going to have a belt and a capacitor that moves it from here to there? This work by the Van de Graaff is what takes the charge from the negative plate to the positive plate, if we could say that. This will never do it here. So if I have a voltage like this, what's going to happen? This may be getting smaller. I'm not going to say that this is not doing that. But that positive charge is doing what? It's pushing positive charge away from that negative plate. So the current must go in that direction. So why did I do it? Because that's the way it is. That's positive charge flowing down. That's positive charge flowing down. So when I apply KCL, it must be wherever the hell I applied to that. Where is it?
On the bottom.
Did I do that?
Oh, that's fine.
Yes.
Oh, damn. I should have been docked here and paid. Right? That's absolutely wrong. That's the way you write it. That's why I write that positive sign right there. Okay? Capacitors are passive, not active. Let's go to the next circuit. Okay? Now this one has teeth. Okay? This is the thing you want to expect from me. Okay, let's draw this guy out. Okay. By the way, this is the last example of this chapter. Then you got plenty of practice on your problem set. And I think this is, you know what? This is your PLC. Just to let you know. The only thing that's missing here is an inductor resistance. Okay, so this is a pure inductor. Think of this as a superconducting material. Okay, so now what we're going to do here is that I got these values of 20 ohms, 80 ohms, 3.5 Henry. This is 50 millifarads, and this is 80 ohms. So now the switch is closed at t equals to 0. And what we're looking for, you got to be careful here now. What are we looking for? We're looking for this current. Okay? And we're looking for this voltage. You know, I used to put them as a function of time. But it's just kind of habits. So, check this out. What this question really means, effectively, is that I got to find what? To answer this question, I need DC of 0 plus, IL of 0 plus. So when I have these, then these will be sort of like obvious what actually happens. And then ultimately, we're going to need these guys. So I'm going to need these to get these two right here. So we want to do this a couple of ways. So how about if I do the first part and then you do the second part? How much time do we have? Oh yeah, we got plenty of time. Okay. Here we go. So what I really need, what I'm interested in is always what? After the switch is thrown. But there's something nice about knowing these guys because it's also in steady state. We assume steady state. So here we go. So the first part I'm going to do here is that I'm going to go after these guys. Okay? So when I look at this guy, I get what? So at steady state, right, assume steady state. And what do I mean by steady state? We know that caps are open, inductors or ducts are short. So if I look at this guy here, I'm going to redraw the circuit. So here I go. So if I redraw this, by the way, I just wanted to say something which I never said before here. You know that during the exam, remember I said that when you had the Thevenin circuit, you should draw one circuit as an open, one circuit as a short, 7 of you SOBs tried to do it on the same circuit, and 7 of you SOBs included that resistor at the load. How long does it take you to redraw the circuit? I don't know. Maybe it was too much time. I just wanted to thank you in helping me grade. Okay? So now, when you do this, you're going to see that there are 2 circuits here. You know what people have a tendency to do? Draw one. I'm going to thank you for the quiz ahead of time. So when we look at this guy, what are we seeing here? We have a resistor. The inductor goes to a short. The capacitor goes to an open. And then I have this resistor right here. So if I look at this circuit here, we're seeing a couple of things. We're seeing that if this is an 80 ohm resistor here, you can see here that this guy gives me what? IL at 0 minus. This gives me VC at 0 minus. So if I look at this guy, you can see that the current of the inductor is what? This divided by the sum of these guys. The voltage of the capacitor, because it's in parallel with the 80 ohm resistor, must be the same. So if I calculate this thing here, the first thing I'm going to see here is that the current of the inductor at 0 minus is then going to be 24 volts divided by the sum of these 2 resistors. So I'm going to get 24 over 20 plus 80 ohms. So that should give me 0.24 amps. But the important thing here is that we don't care about 0 minus, we care about 0 plus. So far so good? So then, if I look at the voltage of the cap, as we did before, we know that that's the voltage across the 80 ohm resistor. So that means then it's got to be 80 times the current in the circuit. Actually, I'm going to go back to this form. So I should get what? 24 over 100. So that should give me what? 2/5, 48 divided by 5. I have no idea what that is. I get 19.2. Again, I don't care about 0 minus, I care about 0 plus. So far, so good. Now, here I come. And I think this is tricky here. So when I look at this now, I'm looking at B, and what we're really looking for here is we're looking for what? I2 V1. Okay, so we're looking for I2 at 0 plus and V1 at 0 plus. So what you're finding here is that now I have my circuit, which is 24 volts. So initially, we know that this guy's current had to be 0. It's not there. And then this voltage has to be the voltage of the capacitor, so we know that it was 19.2 volts. So just by looking at how they behave, we do this. But now, this is a game changer. Right? So what we're seeing here is that as far as the cap is concerned, this is giving us some information. I know for a fact that this current here has to be what? 2.4 amps. Or, sorry, 0.24 amps. And I know that this voltage here has to be 19.2 volts. Right? So I have additional information. So my job now is to do what? I want to apply KCL and relate. Look at my currents here. So if this guy is current I2 here, and this guy is V1, I need to relate these two currents right here. So if I call this V2, I2, I'm also going to call this V2. If I call this V1, I'm also going to be imaginative and call this I1. Okay? So my job is to do what? To relate I1 and I2. I want to apply KVL and relate V1 and V2. So typically, you want to look at nodes where I can relate these guys. Typically, you want to pick a loop that has these two guys in the loop. So let's go to the circuit here. So if I go to the circuit, the first thing I'm going to look at is I'm going to look at this node. So look at that. There's I1 and 2 at this node. So if I look at this node A, let's say, we can say then, at node A, we could see here that I'm going to get what? I'm going to get I2, I1, then I got the inductor current at 0 plus. So this tells me here that I got so the currents coming in have to be the currents coming out. So I got I1, and look what I'm going to do. That equals this. So then I want to have I1 and I2 on one side of the equation. So you see that I2? I'm going to bring it to the other side. If I bring it to the other side again, I get that. That's my first equation right here. Right? So I got my first equation. So this is giving me a system of equations to solve. By the way, this is how you solve for the boundary conditions for a second order circuit. Or I should call them really initial conditions. So then I got to look at KVL. So if I look at KVL, what you're seeing here, I got to relate this voltage to that voltage. So the most obvious choice would be to go all the way through the outside. Okay? If I go all the way through the outside here, then I'm going to apply KVL around outside loop. So if I do that, I'm going to get what? I go minus, plus, plus, so that gives me V1 plus V2 equals 24. So now I have my second equation. So now what I got to do here is that I got to convert this into what? I2, right? And V1. That's what I got to do. I got to convert them. So how do I convert these guys? So if I look at the first equation right here, let me make sure I'm setting my stuff up correctly here. So my first equation, I could see here that I have I2, but I got to convert I1. But how do I get I1? Well, I need the voltage across, right? I'm going to get what? I got, let's see, so I got I2 I'm sorry. I just use Ohm's law. Right? So if I look at I2, or I1, excuse me, it's got to be V1 divided by 80 minus I2 equals IL 0 plus. Okay? So now I got in terms of V1 and I2 here. Now I got to do the same thing here. So I'm looking for V1 here, so I got to convert V2. So if I look at this guy, it's got to be V1, and then according to Ohm's law, it's got to be what? I have an 80 ohm resistor, so it's got to be 80 I1. Let's see, let me make sure. V2 here has to be 80 times I2, and that has to equal 24. I have a system of equations now. If I have a system of equations, then I can now solve this 2 by 2 matrix. So if I solve this 2 by 2 matrix, I get that V1 at 0 plus has to be 21.6 volts, and I see that I2 at 0 plus has to be 30 milliamps. And that's the solution right there. Right? I go from there to there. So let's say this again. Okay, let's look at this again. I have a circuit. You're always going to have to calculate these terms. Why? Because once the switch gets thrown, it gives you two pieces of information. So what you gotta really think deeply here is that if I have these two guys that I gotta solve for at 0 plus, what you have to remember is that you got to think in the language of KCL and KVL. You got to look for the circuit that just says, okay, I got KCL, relate these two together. And you can see that I went to that node, and there they are. And then I looked at KVL, and I says, how do I relate the voltages of these two? Then I do the exact same thing. And then I just convert them into that. So what about the voltage of the inductor and the voltage of the current of the capacitor? Let's change our game here now. Okay? So let's say here, which is essentially what your PLC is, okay? How much can I erase? Can I erase this much right here? Everybody cool? Okay. Not that you're cool, but I mean, you're ready for us to do this, right? So, here we go. So look what I'm going to do. I'm going to erase these. I'm going to erase these. I'm going to erase these. So, here's my circuit. Okay? Here's my circuit. So what am I after now? I'm after IC at 0 plus, VL at 0 plus. So what do you got to write me? You got to write me two equations. Right? You got to apply KCL to do what? You got to write KVL to do what? Do that. That's what you got to do now. Okay? So we're after what? So I'm going to erase these values because we already know that we have them. Okay? So one more time. I'm going to erase these guys because I got them here in the box. Okay? So look at that. I'm going to erase them because they're going to, I know that I have the voltage and that current. So what am I looking for? I'm looking for this guy. I'm looking for this guy now. Okay? That's what I'm looking for. How do I relate these guys now? Right? So if I look at the voltage, how would I get the voltage? So what you're seeing here is that the voltage, it looks like I could do a KVL right in here. The problem is if you do a KVL right in here, I don't have information about this guy right here. Okay? right? If I have this current and this voltage, well, let's just write it out. I got 5 minutes, so let's see if we can do this. So what I'm going to do here, actually, let's just do them in this order. That way we can get rid of this. So the first thing that you want to see here is that I got to relate these two currents here. So the first thing I'm going to do then here is that I'm going to say I'm going to apply KCL, which means I got to relate these guys together. And what you're seeing here is that note, here's where the current is coming for this guy. And if you look at right here, you can see that I have a node right here. So if I apply this node right here, so let's call this, since I called the other one A, so what I'm going to do here is that I'm going to focus on node B. So if I focus on node B, you can see that if I have a current going this way and if I have a current going that way, it looks like I'm going to have a current what? Of I-20 in that direction. So let's apply it. So I'm going to get what? I'm going to get I-20 equals IC plus IL. Okay? Do I know what IL? Now remember, I want to be careful here. I really mean this guy right here, right? Do I know what that is? Absolutely. Right? I know that this is 0.24 amps. Do I know anything about the current of 20? Look at this. Look at this loop. Do I know this voltage? Oh yeah. I know that voltage. What's that voltage? 19.2. So if I take a KVL loop around here, I get the voltage of the 20. I plug it into here, and I get the current here. So what I'm doing here is that here, I apply KVL. And if I apply KVL, you'll see that you get minus what? Minus, look at the polarities here. By the way, the polarities are super important. You gotta really pay attention to them now. So if you do this, you're gonna get minus 24. You're gonna get what? Plus the voltage across here, but that should be what? 20 times I-20. So I get 20 times I-20 plus the voltage of the cap equals to 0. I got the current. So therefore, I got IC here. So if you calculate this thing, I didn't calculate it, so you'll have to help me. Okay? So if some of you have a handy calculator, help me out. So you can see that I-20 should be 24 minus DC, which is 19.2, divided by 20. So therefore, this tells me here that IC of 0 plus must be this number minus 0.24 amps. Can somebody calculate that for me? Anybody have a calculator going?
Yeah. 0.24.
What do you get?
0.24.
Say it again.
0.24.
0.24?
Wait, oh. Never mind, sorry. Nope.
No, I'm gonna say, I was going to say, I hope
Yeah, no.
you get one. So it's this guy right here?
It's 4.8 divided by 20, so it's 2.4 divided by 10.24.
Because we're kind of doing all these calculations based on the instant that switch is closed, right? Can we, by convention, still assume that capacitors like or opening
No.
and opening?
No, the voltage is, but the current in the branch is changing.
I know it's changing, but at the instant that shuts, like we're getting 0, right? I know it's going to change with as time progresses.
Remember, but you saw in the previous example that that wasn't the case.
Right.
Right? It just turns out that this guy is not changing. So if I'm looking at the inductor current, it looks like it's literally right before it's 0, and then it stays 0, which is unusual. Yeah, yeah,
Okay.
the capacitor. But what about the voltage of the inductor? How would you calculate the voltage of the inductor? Well, I know that voltage right there, right? If I know that voltage, I gotta get to this guy. Damn, I gotta go. I got a big lab today. But, by the way, this is your PLC. I should have done the voltage for it. I think the voltage.
Yeah.